Yep. Now, I was at a PD session once that talked about how the color blue is a calming influence. So I thought, you know what?
I can see it.
So I put that up there as a power. It is kind of calming, isn't it? Is it a powerful image?
Well, I mean, electricity is usually that kind of color.
No. It is kind of purple up there. It's definitely blue here. Come and see. That's blue, right? It's not just me? Oh. Blue?
Yeah, that's blue.
Thank you. Okay. So, here's what power is. So I can do a little bit. Power is real super easy. I'll give you some time to work today. If you want, you can do the running up the stairs today too if you want. There's no reason why.
So then what? So then would we have the entire class for tomorrow?
Well, I mean, I'm going to be debating. I would like to give you as much time at the end for sort of exam review and all that stuff, right? So, I mean, yes, but I think we got to be a bit, cognizant of that. So we'll see how things go today. Okay, so power refers to the rate of doing work. How fast the work gets done. Okay.
Yeah.
We are going to have an actual test. What? Probably the first part of that last week of school. Approximately? Yes, I would say almost 2 weeks away from it. Probably like about the 23rd or 24th. Okay, so power is the rate at which work is done. Work and energy.
That's really weird. Like, why do they call it work? Is that like a scientific?
Yeah, it's the definition. Yeah, yeah. Or you could also think of it as the rate at which energy is transferred from one object to another. Like, if I throw the tennis ball and it takes me a long time, right? That's not very powerful, is it? But if I give it the same speed, but do it really quick, well, that's more power, right? I use more. I expend that energy quicker, right? How fast the energy is transferred from one object to another. Did I go too fast?
Nope.
I'll post this on School with you later. You guys know that. So it refers to the amount of work done per unit of time, and mathematically, as a formula, power equals work over time. That's how simple it is. Power is work over time. Right? Power is measured in, does anyone remember? Joules per second, which is known as the, were you away today? Known as the watt, right? Like light bulbs, 100 watts. Right? 100 watt light bulb transfers 100 joules of energy per second. A 60 watt light bulb transfers 60 joules of energy per second, which is why it's not as bright. The 60 is not as bright, 100 bright, right? Pardon me? And this is exactly what Ty was asking. The units of power, given that power equals work over time, or joules per second, right? We define 1 joule per second as 1 watt. James Watt. The guy that was named after the 19th century developer of the steam engine. We also measure power in, if you've got like in a small engine, or even a large engine, measured in horsepower. Interesting thing, Google up why it's known as a horsepower. It actually, you know? It was how much a horse could, how much water a horse could pull out of a well, like in a minute or something. It's like horsepower. Yeah. Not very standard because every horse is different, obviously, right? So it's not a very scientific unit. Okay, so here's the sample question. It's pretty easy stuff.
Listen to the dogs bark.
Brad, are you staying with us here?
Yes.
I don't have a sheet for this. No, I don't think I do. I apologize. Should I just... So the question is, how much power does a 50 kilogram girl, let's use the verb develop, or exert, or use up. What power does a 50 kilogram girl develop while running up a 2 meter high flight of stairs in 0.75 seconds? This is exactly what you're going to do later today or tomorrow. Okay? Your weight does matter because the work done is against the pull of gravity, and the bigger you are, the greater your mass, the more force you need to push yourself up, right? She doesn't matter. The stairs are 2 meters high. Does it matter that she goes like 20 centimeters at a time?
Nope.
No. So she's doing work against the pull of gravity, right? So here's how you do it. Power equals work over time. The work is equal to, now I guess if you wanted to break it down into two parts, you could find the work first, right? Some of you like to do that. The work would be F times D, right? The FW is going to be weight force, which is mass times gravity. So if you want, you could find the work first. You could just go like W equals, I guess, technically, I guess you do the weight force first, mg, then find the work, FD, and then find the power, right? You could do it all in 3 steps if you want, or you could do it like this. The weight force is mgd, right? The weight force is mass times gravity, times the distance, d, divided by the time, 50 times 9.8 times 2, divided by 0.75. It would be, but the force is applied upward, right? So. I mean the what I wrote there. You can find the weight force, mg, and then find the work, right? So what'd you get? 1,306 watts. And if you want to convert that to kilowatts, that'd be 1.31 kilowatts. You should be, yeah. You should know what kilo everything means. Yeah. Kilo, to go from what, kilo means 1,000, right? Like when you graduate from high school, you should be able to handle kilo and centi, you guys. For sure. Centimeters? Hundreds? What? You could put joules per second, but you probably should put what? The conversion. I think it's 750 watts per horsepower, I think. So she's about, yeah. The actual running up the stairs isn't a very good example of your actual horsepower. There's a lot of sort of, like a horse. You don't have, a human is not as powerful as a horse by any stretch. Exactly, yeah. And you're going to find that when you run up the stairs, you're going to even come up like with 0.8, 0.9. I've actually had some of the bigger guys that are fairly athletic have more horsepower than a horse. It's not possible. Like there's a lot of flaws, and it's kind of a fun thing to do.
More horsepower than a horse.
Yeah.
Intense.
Note 1 kilowatt is 1,000 watts. I think I got one more question. Now, the textbook, if you're doing power questions out of the textbook, and this is actually kind of handy, I added this in sort of a few years later. If you want, it's another form of the derivation. If power equals work over time, right, and work is force times distance, what do you see right here? D over T, which is equal to?
Velocity.
Velocity. So another formula that you could use for power would be power equals F times V, exactly. So if you want to use that, you can. Okay, so if you have the speed, you can find power like that. Did anyone look in their car and see if there's a rating for horsepower or wattage or anything from the driver's side door?
It's too cold.
Yes, Brad? Oh, you did look? Oh, yeah? All the time, like in case it changes?
Well, like every car service.
Oh, gotcha.
See what it is.
And does it show wattage?
Does not show.
No, some might.
I'm telling
Maybe like a European car, right?
you. That's supposed to.
Yeah. Maybe like a Mercedes or something other, maybe?
That makes sense.
I don't
Mercedes-
think it works. I
or
don't think
Merce-
it worked out.
No, you don't see. Here's some textbook questions if you want. I think, did I give you some power questions?
Maybe.
Okay. So now, normally what I did, I think I kind of screwed this up. Normally what I do is I go through this handout first before I do the notes. So I screwed that up. Should I do that? Let's do that.
It's not good at all.
Let's go through this quick. It won't take us long. This is basically the same stuff. There's a little bit more background information here. What I gave you was sort of like the bare bones kind of stuff. The quantity work has to do with a force causing a displacement. Work has nothing to do with the amount of time that this force acts to cause a displacement. Sometimes the work is done very quickly, and other times the work is done rather slowly. For example, a rock climber takes an abnormally long time to elevate her body up a few meters along the side of a cliff. On the other hand, a trail hiker who selects the easier path up the mountain might elevate her body a few meters in a short amount of time. The two people might do the same amount of work, yet the hiker does the work in considerably less time than the rock climber. The quantity, which has to do with the rate at which a certain amount of work is done, is known as the power. The hiker has a greater power rating than the rock climber. Power is the rate at which work is done. It's the work-to-time ratio. We know all this already. The standard metric unit of power is the watt. As implied by the equation for power, a unit of power is equivalent to a unit of work divided by a unit of time. Thus, 1 watt is equivalent to 1 joule per second. For historical reasons, the horsepower is occasionally used to describe the power delivered to a machine. 1 horsepower is equivalent to approximately 750 watts. And right? So it sounds like the value for a horsepower is a little bit,
Shady.
it's a little iffy, little-ish. Yeah. Yeah. Basically,
You want to have more response?
it was a marketing scheme, really, right? Yeah. Yeah. Okay, so most machines are designed and built to do work on objects. All machines are typically described by a power rating. A power rating indicates the rate at which the machine can do work upon other objects. Thus, the power machine is the work-to-time ratio for that particular machine. A car engine is an example of a machine which is given a power rating. The power rating relates to how rapidly the car can accelerate the car. Right, listen. Suppose that a 40 horsepower engine could accelerate the car from 0 to 60 in 16 seconds. If this were the case, then a car with 4 times the horsepower could do the same amount of work in 1/4 the time. That is, a 160 horsepower engine could accelerate the same car from 0 to 60 miles per hour in 4 seconds. The point is that for the same amount of work, power and time are inversely proportional. Equations can be guides to thinking about the relationships between quantities. The power equation suggests that a more powerful engine can do the same amount of work in less time. That might be a wonderful test question. You know, I might say something like, a snowblower, I kind of did this yesterday, right? 2 snowblowers, which one can clear the driveway faster, right? Or you've got a 6 horse and I've got a 3 horse. I take 20 minutes, you're going to do it in 10. Right? That kind of thing. A person is also a machine which has a power rating. Some people are more powerful than others. That is, they are capable of doing the same amount of work in less time, or more work in the same amount of time. In the personal power lab that you guys are going to do, students determine their own personal power by doing work on their bodies to elevate it up a flight of stairs. By measuring the force, displacement, and time, we were able to measure our personal power rating. Suppose Ben Pumpeniron elevates his 80-kilogram body up the 2-meter stairwell in 1.8 seconds. If this were the case, we could calculate Ben's power rating. It can be assumed that Ben must apply approximately 800 newtons downward force. Where did they come up with that number? Mass times gravity, 80 kilograms times approximately 10, right, newtons per kilogram, about 800 newtons. It can be assumed that Ben must apply 800 newtons downward force upon the stairs to elevate his body. By doing so, the stairs will push upward on Ben's body with just enough force to lift his body up the stairs. Can also be assumed that the angle between the force of the stairs on Ben and displacement is 0 degrees because, right, straight up, more or less, right, 0 degrees. With these two approximations, Ben's power rating could be determined as shown. 800 newtons is the force times the distance, that's the work, in 1.8 seconds. Ben's power rating is 888 watts.
What a horse.
What a horse. He's more powerful than a horse. Now,
So how powerful is the horse?
735 watts. Now, they did say in the video that Watt overestimated. There's no way that the horse can continue at that rate for an entire time, right? You can be more powerful over a short period of time, right? Which is why that your horsepower rating might be more than a horse, right? When you're running up the stairs and it takes you 1.8 seconds, you can be pretty powerful for that amount of time. But to maintain that speed is virtually impossible, right? Whereas if it's like a snowblower, that's the speed, that's the power rating for that, that's the speed that it operates at, right? The expression for power is work divided by time.
Could be a question, like, say someone gets tired, like halfway through something.
No, I don't think so. It's a good idea, though. Now, since the expression for work is force times displacement, the expression for power can be rewritten as force multiplied by displacement divided by time. And this is that whole bit here where I come up with power equals force times velocity, right? Like we already saw. Right? This new expression for power reveals that a powerful machine is both strong and fast. The powerful car engine is strong and fast. The powerful farm equipment is strong and fast. The powerful weightlifters are strong and fast. The powerful linemen on a football team are strong and fast. A machine which is strong enough to apply a big force to cause displacement in a small amount of time is a powerful machine. Kind of like a big front end loader, right? Can push a lot of snow really fast, right?
Yeah.
What about like a semi truck? How powerful is that?
It's strong, but it's not
It's
fast.
strong, right? But it's not as fast. So it might actually have a lower power rate. It might have more pulling power, but not as much power. More torque, exactly. Okay, now we got two options. I think we should do the clicker quiz. Let's do it?
Yeah.
See what you do here. Come get a clicker. Come get a clicker. Last one, likely. Come get a clicker and a quiz right there.